The other thing I wanted to show you was the comparison between running the just hydrostatic, the inertia relief, and the traditional constraint versions of the model. So I have that opening right now. I created basically 3 copies of the model. And actually, before I do this, let me go back in here. I'm going to reopen the half model. So this is the model that was sent out earlier. It's been loaded. We have everything all set. If I come in here and convert this to a full model, and this is something I'll probably do again before the next session, I'm going to just mirror this like we did previously to create the full model. It mirrored all the groups. So we have mirrors of all of our plate groups, engine, and volume groups here. I'll run a hydrostatic balance on everything. And this is very similar to what we did earlier with the half model. The only difference is that now I've mirrored it. If we come in and go to run the global FEA, there's a results file that we ran previously. Mirrored the model but didn't change the file name. It still says half hull. We'll say, okay, go ahead and overwrite that. And as we check the output here, it's mirrored those 2 degenerate tries. Well, it looks like I made a mistake in trying to show you an error. I think I accidentally fixed it before running. I'll have to open another version of this. Basically, when I ran this earlier, I think in running the hydrostatic balance, it automatically renumbered the FE tags. Previously, when I had mirrored the model and tried to run the analysis, I got an error for no apparent reason. And when I went to view things, everything seemed fine. I started going through the traditional checks. I went through the tools and integrity check, and as soon as I ran element connectivity, which is normally no problem at all, and I knew the model was fine, I saw there were 42,000 elements with connectivity issues, which clearly isn't right. Well, it was the renumber FE tags, and that's usually the first thing you want to do if you see something odd. And I simply renumbered FE tags, and then everything was fine. And that's what I was trying to show you, but unfortunately the model ran properly. Let me see if that happens here. This is just a copy of the half model. So if I mirror it and try and run, it appears to be working fine too. So I can't replicate the error. Oh, here we go. We got a course mesh job failed, but one of them also completed. So let's see which one failed. I expect it to be this one. Yes, course mesh job failed. If we come in and run our integrity check, or element connectivity. Here you see 49,000 elements not connected, which clearly is wrong. We come in, renumber FE tags, and now everything's fine. If I were to run this now, it would run just fine. But that's what I wanted to show you, was that when you see something odd and there doesn't appear to be an explanation for it, always try to use the renumbered FE tags first. There's a good chance that may resolve your issue. So here's the hydrostatic. I have a similar one created. Actually, it's identical. The second one's called IR for inertia relief. This one will get both the hydrostatic balance and the inertia relief run. And a third one where we'll define traditional restraints. So in this first one, hydrostatic, and I've removed 3 of the load cases. We're only looking at the load case 2, the final mass distribution. So I'll go ahead and run the hydrostatic balance on this one. On our second model, we're going to run both the hydrostatic balance and the inertia relief. So we'll get hydrostatic balance started here. Now we'll run the inertia relief. Cautions you that it found something in there. Would you like to continue? Say yes. And for our third model, we're going to use traditional restraints. So I'm going to run the hydrostatic balance first so we can see where the water plane is. And we'll turn on the water plane, turn on the nodes. We'll open the restraints dialog, create a pin connection there, and we will do a Y and Z restraint there, and just a Y restraint there. Turn off these nodes. We're not going to run the inertia relief because we have constraints in the model. So we can get this one running. with the 3 models running, we're using a bit more of our CPU. And as soon as these are done, we can take a quick look at the results and compare them between the 3 different methods. And before the next session, I'll rerun the inertia relief version of the sagging condition with the full model to take a look at that, as well as perhaps change the tolerance on the hydrostatic balance to see if that may have influenced anything. See if the full model has the same deformations that we were seeing in the half model there. One of them finished. That's the third one. So now we can look at the results. For each of these, I'm going to turn off the mirror so we get a better view of the interior. Well, let's first look at the deformed model. Now this is the hydrostatic balance only, and you can see this is a little odd. We're not seeing much in way of deformation on the decks or anything, but a fairly significant, what appears to be trim. And if we look at the scale factor, it's only 1.6, so that's a very large deformation aft, 10 meters in the Y direction aft. So that's not quite right, but this is also not how we're supposed to be running it. There basically wasn't a constraint defined. We don't have any manual restraint nodes, and we never ran inertia relief, which would create the virtual restraint at the CG. So I think it created a single restraint up at the bow when it ran, but this isn't quite an appropriate way to do it. It should have run hydrostatics and inertia relief, which is what we did in the second model. So if we look at this one and view the deformations, now it had to use a fairly high scale value, 189, to see what our values were. And when we looked at the third one, which was the traditional restraints, if we look at the deformed model, again, we get something fairly substantial. So let's look at, if we put each of these in the undeformed condition, and I'll put them all in the default southeast view. So as we toggle between these 3, looking at the first model, the second model, third model, they're basically all the same right now. We'll come back in and we'll turn on our von Mises stress, all 3 models, and to do a quick comparison between them, you can see the one with inertia relief and the one with the traditional restraints are very similar. If you look at the top of the scale for the inertia relief, 3.69 times 10 to the 8th versus 3.73 times 10 to the 8th. If we look at the one that was only run with hydrostatics, we get 1.37 times 10 to the 9th. And you can see that hot spot up at the bow, right up in here, which is also happened to be what was restrained when we saw the deformation plot. If we now come in and reset the scales manually, we'll use a common 0.75 e to the 8th, all 3, just so we get an apples to apples color contour. And let's change that third one. Now as we transition from traditional restraint to inertia relief to hydrostatic balance, the stresses throughout the model look very similar. The main difference is up in the bow region of that first one. If you keep looking in this area, that's where most of our changes are for that hydrostatic one. So the overall solution for the model, the stresses worked out very well, but whatever that restraint was that it created up near the bow had a pretty substantial impact on the results there. Now that wasn't how it was supposed to be run. This isn't really a valid analysis in this case. We should have run it in one of the other 2 ways, either the inertia relief or the traditional restraints. And looking at those 2, we get very similar results.